top filled out, so we're just gonna, I'll take some numbers from you guys and some numbers from you guys, and we'll walk through. So my numbers won't be exactly like yours will be, but we'll walk through. So this is marker that works. So really, it's sodium hydroxide, which is your lye, and your vinegar, which is C2H4O2. They have the energy added here, but really it's not. It's heat that's coming off, right? Because yours got really hot. So really, it should be over here. Got water and NaC2, I don't know what that is, H3O2. Okay, and then we got some heats that came off, which is why they're saying if they show with the energy on this side of the equation, which is why it's a negative number, because it's getting used up. So we'll have a negative delta H. So to find the delta H, we need to remember Q equals MC delta T. That's back from a chapter ago. So we are going to find the mass of the lye plus the mass of the vinegar. So you need to know what your lye was, and you need to know what your vinegar was. So what was your lye?
It was 11.74 grams.
11.74 grams, plus what was the mass of your vinegar?
40.03.
40.03 grams. So in this test one, oh, you have my calculator. If you need it, you don't need it for yours? All right. I guess I got another one, but I gotta run upstairs to get it. All right, so actually I could do this in the back. So I hope I can add this together. 7, 1, 5. So this one, this imaginary one, a mix of yours both, would be 51.77 grams of vinegar and lye together. That's our mass. So that's our M. Our C is going to be the value of the specific heat. In your text it says that vinegar is 4.1. So this is going to be times 4.1. It should be grams, degree C. I can't remember. What's my unit? It should be joules per gram degree C. That's what it is, joules. Times my delta T. So we need to find the final temperature minus the initial temperature. So remember, delta T equals temperature final minus initial. So what was your final temperature?
50.3, I think.
50.3 degrees C. What's your initial temperature?
19.9.
19.9 degrees C. So you're going to subtract that. What's 50.3 minus 19.9? So it changed, delta T is changed about 30 degrees, 30.4 degrees C. So that's going to be my delta T here, 30.4 degrees C. Okay, so now to find out my Q, I'm going to take my grams times the specific heat times the delta T, and I'm going to get a joules of heat that's given off. So again, my numbers are going to be slightly different from yours. 51.77 times 4.1, that number should be the same, times 30.4. This is 645.2.6, blah, 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 blah. But I only have two significant digits here. Here I have 4, here I have 3, but I only get 2. So I'm going to round this to 2 places. So I'm going to look at this next number here and think, is it a 0, 1, 2, 3, or 4? I drop them off to 0. If it's a 5, 6, 7, or 8, I got to round this one up. So it equals 65,000 joules of heat that came off. And remember, it came off, so it should be a negative number. When heat is coming off, it's a negative number. Okay, so we're very close to an answer now. We have the amount of energy that's released with this chemical reaction, but we don't usually use it in joules when we're talking about entropy. They usually measure it in energy per mole. Well, so we have to know how many moles. I'm going to erase some of this. We have to figure out how many moles of sodium hydroxide we have. So if we have, you have to look back and see how many grams of lye you had, so you should have measured that. And how many grams of lye did you get?
Got 1.45 grams.
I'm going to switch markers again. 1.4545 grams of lye. So I want to change that to moles. So I'm going to look at my periodic table, and I'm going to see that if it's NaOH, lye is NaOH, I have to look up sodium. I have to add on 1 oxygen, and I have to add on 1 hydrogen, and I'm going to cheat and see how much that weighs. Thank you, Erin, for doing your lab so nicely a long time ago. And that is 40.0 grams in 1 mole of sodium hydroxide. There's that many grams in it, right? That's from the periodic table. So now I have how many moles I have. Remember, your number's going to be slightly different. 1.45 divided by 40.01 equals 0.036. I have 3 significant digits here and 4 here, so I get 3 here. 362 moles. Okay. So now we just need to find out, we can calculate the entropy, because entropy is expressed in energy per moles. So I'm going to take my energy, which is 6,500 joules, and it's usually in kilojoules per mole though, so it doesn't say to convert that there to kilojoules, but I think we have to convert that to kilojoules. Yep. So remember, kilo, it means 1,000. So I have to equals, I should times it by, there are 1,000 joules in 1 kilojoule. So I'm going to move my decimal place over 3 places. So this is really 6.5 kilojoules. And then I'm going to put it over my moles. So ran out of space again. So I'm going to have 6.5 kilojoules in the 0.0362 moles. So if I take those two numbers, again, your numbers are going to be slightly different from mine. 6.5 over 0.0362. That gives me, I only have 2 significant digits. So 179 rounds to 180 kilojoules per mole. So what is, and it's heat that's coming off. So my delta H is really negative 180 kilojoules per mole. So yours might not have been that much because I mixed both of yours together. Really, if your scoop was bigger and you had more grams of lye, maybe you got more heat. But if you had, I mixed your two together, if you had less than that, it should be around 100, so it's kind of high. All right, what does that tell you? That tells you that we got heat off of this, and we can measure that heat, and that heat is a negative number only because it's coming off. So if that heat would have been going into something, it would be positive. But because it's coming off, it's a negative number. They just do that for clarification. Okay, so let's talk about when a reaction, this is page 417, when a reaction is exothermic, energy is kind of a product. So I erased my equation here, but on your lab it's written as a reactant. It's really not, because it's an exothermic reaction, so it should be on the product side. Heat is coming off. If the reaction is endothermic, energy is considered a reactant, so it should be on the reactant side. You can kind of think of it as, this paragraph on the top of 418 is kind of helpful. We can think of it as the heat in chemistry. Heat is kind of like the potential energy that's stored in a chemical bond of a substance. So what happened is I took lye and I took vinegar. There was potential energy stored in those bonds, and then they mixed together, and that energy was released. So it was stored in the bonds, it mixed together, and when it mixed together, those bonds rearranged, and the energy came off. So it's energy that's stored in the bonds. That's how this ties into chemistry, even though it kind of feels like physics. Kinetic energy, on the other hand, can be thought of heat that comes off. So potential energy is stored in bonds, and when it comes off as heat, it's kinetic energy. Remember, kinetic is more energy that is in motion. Potential stored, kinetic is your heat that's here. Okay, the energy stored in a substance is called the enthalpy of that substance. And so the change in enthalpy, or the delta H, is the energy that is in a chemical reaction. So again, for positive H, you have endothermic reactions. That means it's going in. Negative H is heat that's coming off. Let's do, I have just doing sample 3-2. Time, we only have 15 minutes. Let's do, so there's different ways to calculate, because enthalpy is the energy that's stored in the bonds. There's different ways historically how they have calculated enthalpy. So I have to show you the long way, because there is one of these that are on the test, but don't zone out completely, because there's an easier way. So I'm telling you now that there's hope at the end of this. There's an easier way. We'll continue to do the easier way, but you have to learn the long way, because there's one on your test that says show it using the long way. Okay, so if you want to determine the energy that is stored in the bonds, you have to use table 13.1. It's on page 424. All right, so the first long way is delta H is the energy to break bonds minus the energy to form bonds. Okay, so if you use table 13.1, I actually wrote on the top of mine, it's bonds broken minus bonds formed. Okay, broken minus formed, because the spoiler is later on it switches. And this is the long way. Okay, so we're breaking bonds and we're forming bonds. We're mixing two things together. So what we need to do is you need to add up all of the energy to break all your bonds, and then you need to subtract all the energy needed to form bonds. What does that tell you? Darn it, you need to know every single bond that you have in all of your products and all of your reactants. That's the long part. So to do that, you need to kind of draw your bonds. That means go back a couple chapters in your brain. Do you remember how to draw things? I hope you do. So let's do example 13.2. To make ammonia, nitrogen and hydrogen are reacted according to this equation. N2 plus 3H2 turns into 2NH3. And, I'm too lazy to write those anything. So it says, what's the delta H for this reaction? And is it endothermic or exothermic? So if your delta H ends up being negative, it's going to be exothermic. If your delta H is positive, it's endothermic. So you have to remember how do you draw N2? So remember, look on your periodic table. Here's my periodic table. And you have to find where N is and find out how many dots and dashes are, and it's in row 5. So that means it has 1, 2, 3, 4, 5. And there's 2 of them stuck together. So here, let's give my other N. 1, 2, 3, 4, 5. They're not happy, so it probably doesn't look like that. So I gotta move these things. Here goes here. And here goes here. Still not happy. So probably 1, 2, 3, 4, 5. So that means I'm gonna have to move another set here, and then this one will probably go over here, and these ones go over here. Hopefully you remember how, if you need to do a Lewis structures thing again. So what does that mean? It means that it's an N with a triple bond and another N. Okay, so looks like not too hard of a problem, but I have to draw each one, and then I have to figure out which one of these bonds are gonna break. And then hydrogen's easy, so I have hydrogen only has 1 and only wants 2, so that one's easy, but I have 3 of them. So that, and it's gonna turn into an N that has 5, 1, 2, 3, 4, 5, and 3 hydrogens around it. So 1, 2, 3, okay. But I have 2 of them. So I have an N with another H, and an H, and an H. So every single one of these bonds needs to be taken into consideration. This one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these ones are breaking, these ones are forming. So I have to keep track of all of them. So what's going to happen is you're going to take your energy to break minus your energy to form. And it's the sum of. So it's an order of an operations problem. You have to add all these together and then subtract, add all these together. So just make sure you use your parentheses. And again, if you set them up correctly and you do a math problem, I probably will give you most of your credit because they're kind of long. Okay, so what happens? For this one, we're going to use the energy of the bonds to break. So these ones are broken. So it's going to be the delta H is going to be my balanced equation. I have 1 mole of this. So 1 mole times, it's an N triple bond. So I have to look at the page 424. I have to look for an N triple bond, and it's 942 kilojoules per mole. 942 kilojoules per mole. Plus, I have to find the H bond. It's just a single bond. So I'm going to look at the chemical bond of that, and I have 3 moles of that, plus 3 moles of 432 kilojoules per mole. So I have to add that together, and then I'm going to subtract the energy that it took to form them. I have 2 moles of an NH bond. So it's one N. No, I don't. I have 2 moles of this, but it's, for every mole, I have 1, 2, 3, 4, 5, 6 of that. So I have 6 of those. So I have 3 moles of that because there's 3, and there's 1 of those, and there's 6 of the N of H bond is going to be 386 kilojoules per mole. So that's why you have to draw it. You have to figure out what they are. You have to draw them. You have to count them. Okay? And then you're going to take 1 times 942 plus 3 times 436 minus parentheses 6 times 386. And you're going to have to see, do you have a positive or a negative number? You put that into your calculator and you're going to get, hopefully, negative 78 kilojoules per mole, which is the form that we had in our lab today. So the question said, what's a delta H? That's my delta H. And then it says, is it endothermic or exothermic? Is this endothermic or exothermic?
Exothermic.
It's exothermic. If I have a negative delta H, it's going to be exothermic. So there's going to be one evil question like this that you have to actually draw them. You have to actually count how many of the things you have, and you're going to use this table. And it's a really long problem. And don't forget to say, is it endothermic or exothermic? And then next week I'll show you an easier way that talks about Hess's law and makes it easier. So then don't hate me and you come back. Okay?